Okay, welcome everyone. So this is the morning session of the final day of the ICBS. The first speaker is Professor Andrei Caldararu from University of Wisconsin-Madison, who is telling us a gentle introduction to categorical enumerative invariants. Let's welcome.
Thank you very much, especially to the organizers for this wonderful conference. I'll be talking about some work that I've been doing with my former student Junwoo Tu, who's in Shanghai Tech, and this is a good opportunity for me to visit him, and with Kevin Costello. This is our latest paper on the subject from last year. And our work is aimed at defining some invariants which we call categorical enumerative invariants, and I will abbreviate this because it's a long name as CEI. And what these are, these should be some invariant associated in the simplest way to a Calabi-Yau category C. So I need to first, since this is a fairly expository talk, I need to tell you what a Calabi-Yau category is. And you should think of a Calabi-Yau category as something that looks like maybe, for example, the derived category of coherent sheaves on X a Calabi-Yau manifold, smooth compact Calabi-Yau manifold. But there are other very interesting examples. You could take C to be the Fukaya category of a symplectic manifold. This would be another example of a Calabi-Yau category to which our theory would definitely be, it's important to apply it. Or yet another option would be the category of matrix factorizations of X a quasi-projective variety and W some function from X to A1. So these are all examples of Calabi-Yau categories. So part of the strength of the theory that we're trying to develop comes from the fact that you should not particularly care where your Calabi-Yau category comes from. So in fact, the original motivation for our trying to develop these invariants was to try to understand the relationship between homological mirror symmetry and enumerative mirror symmetry, and that's what I'm going to try to explain to you now, where this comes from. So I want to tell you a little bit about the history of mirror symmetry. And the idea is that the first version of mirror symmetry that became interesting to mathematicians happened in around 1992 with this paper Candelas, De La Osa, Green, and Park, where what the prediction was that to count curves on some complex manifold X, you solve a differential equation governing the variation of Hodge structures on a different manifold X hat. So this X and X hat are not related. In fact, they don't even have the same topology. They're very different spaces in all respects, but somehow physicists predicted that if somebody gives you a space X, let's say a Calabi-Yau 3, and you want to count, for example, rational curves on this variety, this was a long-standing problem in algebraic geometry for many, maybe at least 200 years. The physicist's prediction, this is a physics paper, was you need to first find your family of other manifolds here, which are called the mirror, and then for this family of manifolds, there's a natural differential equation that you can write down that discusses how the Hodge structure of this X check varies in a family. You solve this differential equation, you do a little bit of magic, and you obtain a solution which is a power series whose coefficients are the counts of curves on X. So in the beginning, this was completely impossible to understand for mathematicians even why this would be true. It took probably at least 10 or 15 years till we mathematically were able to prove this. This was proven later, about 10 years later, by Giventhal and Yau and collaborators. All right. Now, for mathematicians, in the beginning, there was even a big problem understanding what is the relationship. So for physicists, there was some kind of physics way of saying this X and X check are related. But from a mathematician's point of view, there wasn't even a statement about what's the relationship between X and X check. And then maybe let me call this version of mirror symmetry enumerative mirror symmetry, because it solves an enumerative problem, counting how many curves there are. The second story happened in 1994 with Kontsevich's address to the ICM when he received his Fields Medal. And what he said was the physics relation between X and X check is encoded by the statement that the derived category of coherent sheaves on this X check, so on the second one, the one where you solve the differential equation, should be the Fukaya category of X. So for those, if there are experts in the audience, you probably know this is a weird statement, and this, as stated, is not quite right. Bear with me and leave this as a kind of a vague statement that for now just as motivation, and I will explain in a few minutes how to make this statement more precise. But anyway, Kontsevich predicted that there is this this is at least more or less a mathematical, it was at the time a more or less mathematical statement. Nowadays it's a purely mathematical statement, which tells us that if you want to solve the problem of counting curves on X, which is what in the beginning we started out trying to do, what you should do is you should look at the Fukaya category of X and find some other manifold X check whose derived category is the same as the Fukaya category. That would be the mirror. And once you have done that, somehow, magically, from this equivalence of categories, which is just, it's a complicated statement about some categories, you should be able to extract the fact that the Gromov-Witten invariants, these counts of curves on X, should be the same as solutions of the Picard-Fuchs equation for X check. That was kind of Kontsevich's amazing intuition. And he had a physics reason for this. Just because there's a big physics component of this conference, I want to say that the explanation was essentially that these categories describe the open strings in some physics model, and the counts of curves and the solutions of the differential equation count coefficients of the closed strings in that physics theory. And somehow the main intuition would be that the open strings, the open string sector should determine the closed string sector. So the idea is this is somehow some statement that in some incarnation of physics, this x and this x check determine both something called an open string theory and a closed string theory. And if somehow you magically manage to arrange that the open string part is the same in the two constructions, then the closed string parts should agree. All right. So Kontsevich quite explicitly stated in 1994 that this should be true, that the open string should determine the closed strings. And in practice, what he suggested was that, so Kontsevich suggested that one should be able to extract Gromov-Witten invariants of X from the Fukaya category of X. So the Gromov-Witten invariants, these are what is the formal name of the curve counts. And somehow the whole idea here was that you don't actually really need to know the space X to be able to calculate the Gromov-Witten invariants of X. All you need to know is this Fukaya category, some construction in symplectic category. But this category, in principle, contains less data than the space X itself. And so if you somehow are able to extract the Gromov-Witten invariants directly from the Fukaya category as an abstract category, then if you have established such a relationship, you should be able to feed into the same story the derived category, which presumably is easier to understand, and calculate the same numbers. So that was the idea. So you want to calculate the curve counts. Those should be tautologically extractable from the Fukaya category. But instead, we can represent the Fukaya category as a derived category of something. And then this we might be able to understand better because we have techniques from algebraic geometry. And then from this category, you apply whatever machinery you applied here, and you obtain the numbers you want. So this was the original motivation. And you can see now that this is exactly very much what we are trying to do. I'm telling you, I'm trying to extract from some Calabi-Yau category, like the derived category of X, or the Fukaya category of X. I am trying to extract some invariants. Now, you might also notice that it's 31 years later. So it's been a long time coming. So it's not a very easy problem. And there has been a lot of progress. And we hope somehow that our paper is kind of the ultimate definition of these invariants. But there was some earlier progress. So some contributions, historical contributions to this problem are the following. I would like to mention some of the work that has been done. So in the 2000s, there were some interesting works that I want to mention. So there was, first of all, Baranikov-Kontsevich gave a definition, of CEI that works for genus 0. So they have a theory of something called variations of semi-infinite Hodge structures. So it's a generalization of classical variations of Hodge structures. And in their approach, from a variation of semi-infinite Hodge structures, they are able to extract some numbers which in this picture should correspond to counting curves of genus 0 on X. Now I want to emphasize that this is already an infinite sequence of numbers. It's not just one number. So for every Calabi-Yau threefold, for example, you can count how many genus 0 curves there are of degree 0, of degree 1, so of degree 1, like straight lines. Then you can ask how many quadrics there are, how many cubics there are, and so on. And those are very interesting numbers. So this is a lot of information and great progress. And following on this idea, in the 2010s, there is work by Ganatra, Sherutz, and Peridon. Perutz and Sheridan, where they prove that in certain instances, homological mirror symmetry, I should have explained, this is called homological mirror symmetry. Homological mirror symmetry implies enumerative mirror symmetry in genus 0. So by now, so these guys have accomplished what we were trying to do, basically to explain how Kontsevich's intuition about homological mirror symmetry determines or implies enumerative mirror symmetry, but only for genus 0 curves. So all these computations, the very first question that you ask, are you counting things in genus 0 or in higher genus? And the solutions of this differential equation really were only for genus 0. So the original Candelas, De La Osa, Green, and Park were only genus 0. And okay, so this is what we know, and essentially you could say that up to maybe some technical difficulties which might still need to be solved, but they are related to the definition of the Fukaya category, the problem is essentially solved in genus 0. Now, also around 2004, 2005, there was a completely different direction of works by Kontsevich-Soibelman on one hand, and Costello, the main work being Costello, being he introduced, so using the works of Kontsevich and Soibelman from before, Costello, the main result was he gave a definition of CEI in arbitrary genus. However, his definition is completely non-constructive. So it defines some numbers, but if you ask Costello at the time, hey, compute for me even the simplest such number, would say I don't know how to do it. Not because it's a computationally difficult problem, but because there were steps in the construction which were not effective. They were not something that you could program into a computer and ask it to do it. And then the 2024 papers following a bunch of 2020 and papers, Costello, myself, we wrote a series of papers about with an effective construction. So if you read the paper that is listed there, you should be able to extract, if you give me in some reasonably efficient way the category, you are in principle able to compute if you have a big enough computer. Big enough computer really means a very big computer, but at least it's an effective construction. So this is the story, and I want to tell you a little bit about what goes into this construction. So any questions at this point? This was intended as a general overview of what the story is. Yeah? No. So so there is a big conjecture. So I'm going to state it schematically, but the conjecture should be that the CEI theory applied to the Fukaya category of X should be Gromov-Witten invariants of X. This is what you're asking. This is definitely not tautological. So we define some invariants, but it's not at all clear that they are. I mean, they are definitely intended to be that. And for this, we have some theorems, but the answer is far from known. So let me maybe state what's known. Yes, for X being 2 torus. So this X has to be just a symplectic variety. So I can take the 2 torus with its obvious symplectic structure and any complex structure. And genus 1 and genus 2, this we can prove by direct calculation. So these are some horrible, enormous power series, and the fact that they match is good indication that this works. Other situations that we know, X equals to a point and any G. So this theory recovers the full intersection theory on moduli spaces of curves. So it's already quite powerful. We also, and now there's a claimed proof for symplectic varieties with only one Lagrangian. So it's a bit restrictive, but this should not be a huge problem. And this has been claimed by De Schmuck and 2 co-authors. Sorry, I forget now the name. Hopefully I will remember their names. So this is definitely something that is it's probably the biggest question in the subject. So, but yeah. If this thing works, maybe let me emphasize this. If this thing works, one of the really nice things is it gives new definitions, uniform definitions for many. Every time you see an enumerative invariant showing up in mathematics in various contexts, it always has its own definition, and it's always very technical. So when you plug in the Fukaya category, you're expected to get Gromov-Witten theory out. So you need to prove that, but if this works out, you could just say Gromov-Witten theory is whatever you get from the theory when you feed Fukaya category in it. What you get here from the derived category of X, in genus 0, you should be getting those solutions of variations of Hodge structures. But in higher genus, you should be getting fancier invariants which have not been defined previously in mathematics, but which in physics go by the name of BCOV invariants, Bereshadsky, Chakotay, Oguri, and Vafa invariants. So they are the higher genus analogs of the solutions of the variations of Hodge structures. These invariants applied to matrix factorization categories in genus 0, these would recover Saito's theory, Kyoji Saito's theory associated to singularities of the potential. And in higher genus would be something that's called FJRW invariants in enumerative theory. So this should give rise to Giventhal-Saito theory and FJRW invariants. This should give rise to BCOV invariants, and this should give rise to Gromov-Witten invariants. So the theory is extremely powerful. At the moment, of course, we can't really prove any of these equalities, but you first need a definition of something to prove that something is something else. All right. So now I want to give you some intuition, because I have been lying all along about what goes in the definition of this. And since I haven't erased here, I can quickly fix my problem, because I need to say this will not be associated just to a category, plus extra data, which is called a splitting of the Hodge filtration. So it turns out this was first kind of observed, but if you read it carefully, it was not fully understood by Kontsevich, Soibelman in their original paper. But then Costello was the one who made it very clear that the data that's needed to define these invariants is not enough to know just the category. You need to know the category together with this data called a splitting of the Hodge filtration associated to this category. This is called a splitting of the Hodge filtration because in the geometric setting, which is this one, the data that you need is really a splitting of the Hodge filtration of this complex manifold X. So maybe now you might ask, okay, well, but then homological mirror symmetry didn't tell you anything about the splitting. It only told you about this is equivalent to that. How do you make sense then? How can you even say that this equivalence should imply invariance here equals to invariance here? And the answer is, I've lied here as well in the following sense. The Fukaya category, for people who do symplectic geometry, the Fukaya category is not defined over the field of complex numbers. When you define the Fukaya category, the very first step that you do is you need to introduce something called the Novikov ring and the Novikov field. And this is a category that is defined over the Novikov field. Think about the Novikov field as something like, so I'm going to simplify things a lot, but you can think about the Novikov field is kind of like C round bracket Q. So, and this category lives over this field. What that means is that all the morphisms are modules over this field. But in practice, intuitively, that means that you should really think about this Fukaya category not as one category, but as a formal family of categories, which depends on a formal parameter Q, right? And this Q lives in a small puncture disk, the spectrum of this field. Now, that means that you don't get just one category here, you get many categories. So you might ask, okay, but here there seemed to be just one category. This was well known to people in mirror symmetry. Mirror symmetry is not about one space, it's about a family of spaces. So you should really find a family of spaces XQ and such that the derived category of the coherent, if you imagine that the Q's actually that these Q's live in some convergent power series, not just in some formal power series, that would mean that you can evaluate this Q at some finite value. All these categories should be equivalent to all these categories. So you've got a family of complex manifolds, and I look at all their derived categories, and here we have a family of Fukaya categories. Now, it turns out that this family of categories comes with a God-given splitting. So this has a natural splitting. For those of you who know about this, it comes from the flatness of the Dubrovin connection. You're looking at the splitting that is monodromy invariant under the Dubrovin connection on the Fukaya category. Imposing the same conditions that this Dubrovin connection induces on the splitting on this side singles out a particular splitting for you, and it's with respect to that particular splitting you should calculate the invariance. So this is a mouthful, so I would like to give an example so that people can understand a little bit. So we're going to take it down to a relatively elementary level, and let's say let E be an elliptic curve. Just good old elliptic curve over the complex numbers. Then there's an exact sequence that looks like this. Okay, this is completely naturally defined on every elliptic curve. Here and here we have two one-dimensional vector spaces. Of course, everybody knows elliptic curve, genus 1. You can calculate the genus either like this or like that by Poincare duality. By Serre duality. These two are one-dimensional vector spaces. This is two-dimensional vectors. This is the two-dimensional vector space of middle cohomology of a torus. Okay? Now, what is the splitting of the Hodge filtration? You can think about the Hodge filtration as being the filtration here, which has as sub this and as quotient that. Very obvious. And the splitting of the Hodge filtration is splitting this filtration, meaning you want to look at a map, a linear map, that goes from there to there. So geometrically, what you have is here you have a two-dimensional vector space. In here, you have a line mapping the image of this line of H1, of H0 omega 1. So this is this line. And the image of the splitting has to be any line, any other line that is not equal to this line. Okay. So you can actually see that the space of all the possible splittings is an A1. Because you're looking at lines in a two-dimensional space, that's a P1, and you don't want them to be equal to the point corresponding to that line. Now, every Hodge theorist that I've talked to, when they see this, they get uncomfortable. They say, what do you mean splitting of the Hodge filtration? There is one God-given splitting of the Hodge filtration, and that's the one you should use. The answer is, yes, there is one when you're working over the complex numbers, and that comes from complex conjugation. So one choice is to make this dotted line, the image of this, to be the complex conjugate of the straight line. So because these spaces, when you work over the complex numbers, are complex vector spaces, they have a concept of conjugation, you can take the complex conjugate of this line, it's another line, and take that to be the image of the splitting. And if you read Griffith and Harris, there is no discussion that you could ever take any other choice. In fact, most definitions of a Hodge structure put this condition that HQP equals to HPQ conjugate. But this is not the only choice. And I want to super emphasize this fact. In fact, there are many choices, and for mirror symmetry, we need a different choice. Why do we need a different choice? Maybe let me try to explain this. When you look at this complex conjugate splitting, you are interested in how it varies in a family of elliptic curves. And because of this complex conjugation here, you are actually introducing a non-holomorphic variation. And when you have if you introduce this non-holomorphic variation, every construction you're going to do in the family of all elliptic curves, like here, you're going to end up with results that are non-holomorphic. So this is going to be a huge problem because what you're trying to calculate essentially is this Gromov-Witten potential, which is a power series with coefficients, all the Gromov-Witten invariants, and that by definition, if it's a power series, has to be holomorphic. So the correct choice turns out it comes from this Fukaya category construction with the Dubrovin connection. The correct answer is actually to choose the correct choice is you want to say that you are close to the cusp, to the point where the elliptic curves degenerate into a nodal cubic, and that you are choosing your splitting to be monodromy invariant. The image of the splitting should be the monodromy invariant subspace here under monodromy around the cusp. Not going to go into the details, but I wanted to emphasize this story. I remember the name of the two co-authors. I wanted to write this. So Hirschi and Hüttenberg. This is very recent work. I mean, the claimed proof was a month or two ago. It's not yet on the archive. All right. So now I want to give a very brief sketch of the construction of what the construction of these CEIs is. I think I got 20 minutes left. So I want to give you an intuition of how to define the CEIs and where, why do we need this magic splitting that it was not apparent at all in the beginning, why we need it. So this is going to be a very brief sketch of the construction of the genus equals to 1, n equals to 1 invariant. So when I say genus equals to 1, n equals to 1 invariant, imagine that you're thinking about, so this would be analog of what in Gromov-Witten theory would be called genus 1, n equals to 1 invariant. You're doing some kind of integration on some x with some beta, and here you need to insert some class alpha. So where this alpha for Gromov-Witten theory would be some class in the cohomology of x. So for those of you who have seen definitions of Gromov-Witten theory, what that means is this in Gromov-Witten theory, so I'm recalling what the definition of Gromov-Witten theory is. This would be the integral over M11 bar of x beta. You take the virtual fundamental class here of F1 upper star alpha. So what is this notation from Gromov-Witten theory? I'm going to very quickly start ignoring the beta, but imagine that it's there all along. This beta kind of comes in, is where it's related to the Novikov field story. But the main idea is that somebody gives you the space X on which you're trying to calculate the Gromov-Witten invariant, and you construct out of it a new space, which I'm going to call just M11 bar of X, and I'm going to put the beta as being implicit. And this is a space of all maps from a curve of genus 1 with one marked point into X. And as such, it has an evaluation map to X, which is simply somebody gives you a map from a curve with a point on it to X. You evaluate the map at that point. Now, it's a very classical thing that this also has a map, a forgetful map the other way around to M11 bar, to the moduli space of elliptic curves in this case. All right? So the Gromov-Witten invariant that we are talking about here would be you start with a cohomology class here, you pull it back to here, and then you integrate. Think about the alpha as some kind of cohomology class which gives you some restrictions of where the curve of genus 1 you want to pass through, maybe some divisors that you want it to intersect some divisors. And then you're counting how many curves of genus 1 with one marked point are such that the marked point hits the divisor, for example. Now, I've introduced now this map to M11 bar because this will be quite important for us. So in Gromov-Witten theory, people very early on understood, it was Kontsevich and Manin that understood that it's much more useful, instead of going down to a point, think about that integral that I wrote down as going down from here to a point, it's much more useful to factor the process of going down to a point through M11 bar. And the idea is they define something being something called a cohef-T, which is the sequence of maps. Think about it as maps from the cohomology of X to the cohomology, or maybe let me just say, in this case, it's just this map for us. So you really need a sequence of maps, but for us, it's the map to the cohomology of M11 bar, which takes alpha, goes to P lower star, F1 upper star, So the idea is that somebody gives you a cohomology class on X, and that produces for you a cohomology class in M11 bar. And then later on, if you know this map, you're done, because to calculate the Gromov-Witten invariant, all you do is you have to integrate that cohomology class on M11 bar. All right. So now what they set out to do was to understand the what is kind of crucial about this map. So in fact, they realized that it's not just one map, it's a sequence of maps. So maybe let me write what that is. It goes from maybe let's call it omega g n, which goes from h upper star of x tensor n to the cohomology of m bar gn. And what that does is, if I have alpha 1 up to alpha n, it goes to p lower star of f1 upper star alpha 1 cup fn upper star alpha n. So you give me, if I'm looking at mgn, I have n marked points, I have n evaluation maps, I have n cohomology classes here, I pull them back, cup them together, and then push them down to mgn bar. So this is what the coheft is. And the magical thing that was known to Kontsevich and Manin already in the mid-90s is that these maps satisfy all kinds of very nice conditions, in that if you glue points on what's special is you can take a curve of genus G with n marked points and another curve of genus G prime with n prime marked points. You can glue together two of the points, and you get another thing in the boundary of mg1 plus g2 and 1 plus n2 minus 2. You get some bigger, some maps, some such gluing maps, and these evaluation map, these coheft maps play well with these gluing maps. That's why they call it a coheft. It has to do with, it's a cohomological field theory. The field theory here is exactly talking about the fact that the maps play well with respect to these sewing maps. All right. So now let's try to understand what is special about this coheft. So this coheft has some good stuff and some bad stuff. On the good part, one of the nice things is it. Actually, before I discuss this, let me just say about there's another way to write this map omega gn. Instead of writing it this way, it's nicer to write it as homology of mgn bar tensor cohomology of x tensor n, and with values in, let's say, C. Right, all I'm doing is I'm taking this vector space and dualizing and putting it on the other side. All right, so the good things about this is it can work with homology classes on mgn bar. So you'll see in a minute that this is kind of the, in fact, ultimate goal of what we want, because this is a compact space. We can then integrate on it down to a point. So since we have homology class, this space is compact, we can basically integrate against the fundamental class of mgn bar. So mgn bar has a fundamental class. That's a good thing. On the other hand, there's a bad. it only works at homology level. These constructions take some homology class here, in other words, a closed chain in MGN bar. And the cohomology class here, if you want to think of the RAM cohomology, that means a closed form and produce a well-defined number. That's nice. But it turns out that there is another construction which starts with a Calabi-Yau category in general. This was the original work of Kontsevich, Soibelman, and Costello, that 2004-2005 that I was talking about. From a Calabi-Yau category, we can construct something called a TCFT. This was the result of a completely independent investigation by these guys. So it's a different type of field theory. It's called a topological conformal field theory, which is the data of some maps like this, but which look very different in some sense. It goes chains on MGN. These are singular chains on MGN. Tensor chains, Hochschild chains on this category with values, again, in C. This is tensor. So, what is in this story? So this story was understood fairly early on, and it's very clear how to do it now. It involves some combinatorics of ribbon graphs. I'm not going to say much about this. But the good thing about this is it works at chain level. So notice, magically, I'm allowed to put here even non-closed chains in this theory. So these don't have to be closed. The result need not be the same if I change by exact chains. But the bad here is not obvious how to extend to MGN bar. So notice that here I never put the bar here. So the point is that the Calabi-Yau category alone, if I don't have the data of the splitting yet, only gives me the data of how to do something like, if you want, naively, integrals on chains here, but without the bar. I'm allowed to integrate, I know how to integrate things on chains defined in the interior of M11 bar, but not on all of M11 bar. On the other hand, it allows me to put in here things that are not, I'm allowed to start with things that are differential forms on X that are not necessarily closed. Okay. So now I want to use the remaining 7 minutes to show you how the splitting allows me to extend from MGN to MGN bar. So it turns out this is completely not obvious in the beginning, but the data needed to extend this field theory from integrating on chains on MGN to integrating on chains on MGN bar, the extra data that's needed is exactly the splitting. This was Costello's great realization in 2005. And to do this, I want to do a very concrete example. So let's work with this theory in the Gromov-Witten setting. So imagine that somehow we were able to do this for the Fukaya category. At the moment, we don't know how to do this for the Fukaya Fukaya category. And that is the biggest problem with proving that Gromov-Witten invariants are equal to CEI, so the Fukaya category. We don't have enough technical tools for the Fukaya category, but let's pretend that this would work. So what you should imagine now is that somehow we've got this magic space M11 bar of X, which maps down to X, and it maps down to M11 bar. And I am doing this pull back, push forward. Sorry, I had already this diagram here. I want to draw for you what M11 bar looks like. This is what M11 bar looks like. Hopefully everybody knows the moduli space of elliptic curves is P1 if you ignore, we're working with rational coefficients, so we can ignore safely any kind of torsion in homology. So from the point of view of rational homology, M11 bar is just a P1, i.e. a sphere over the complex numbers. It has one special point, and this is the point that corresponds to the nodal cubic, the point that is the boundary of M11. So the extra point that I have to add to compactify M11, the limit of all elliptic curves. Now, the idea of the CEI definition is to draw a little circle of some small radius around this cusp point. And let me call this cycle, well, actually, I have colored chalk. I'm going to I'm going to decompose M11 bar into two parts. One is everything outside of this disk. And maybe I'm going to call this A. And then everything inside the disk, which I'm going to call B. So if you look at what we were trying to calculate, the Gromov-Witten invariant that we wanted, this Gromov-Witten invariant of alpha, of some alpha, which is a cohomology class on X, should be the integral on M11 bar of P lower star F upper star of alpha. Okay. So now I can rewrite this integral as a sum of two integrals. I simply integrate over A and over B. Right, so I decompose the integral, which would be the integral on the whole sphere, into two integrals, one being the integral on the yellow part and one being the integral on the red part. The integral on the A part, the nice thing is this is already computed by the TCFT. Right? If you look, this A is a chain completely, it's not a closed chain, but it's a chain that's completely contained inside MGN. It doesn't touch the bad part of the moduli space, the boundary. So this, in principle, the data of the category already tells me how to calculate this guy. The question is, how do I calculate this guy? The problem is that the fields, the TCFT, the stuff that comes out of the category does not tell me how to do that. I don't have enough information. But one thing that the TCFT does tell me is it tells me some very strange information. Namely, it tells me, so the TCFT still tells me how to calculate the integral on the boundary of B, which is this circle of anything that I want. So P lower star, F upper star of some beta. For any beta in the cohomology of X, which is chains of my K. Okay? Now, we all know Stokes, and we know that this will say that this is the integral on B of P lower star, F upper star, d beta. Okay? So, what that means for us is something something very non-obvious. Notice that this B does not need to be, it's really important that this B does not need to be closed. If it was closed, then this integral would be completely zero, so this would be a non-interesting quantity. But this B does not need to be a closed form, so we can still evaluate this integral. So what that implies is that the operator that goes from beta in forms on X to integral on the boundary of B of P lower star, F upper star, beta is a closed operator. It is the evaluation of the original form that we want, P lower star, F upper star of something, commuted with the operator D itself. So that, i.e., homologically trivial. And it turns out that it's the splitting S gives exactly a trivialization of this operator. And this is exactly what we need in order to evaluate this integral. I'm sorry, it looks like I'm a bit over time. I'm happy to answer questions, but
First, let's thank the speaker. Are there any quick questions?
yeah.
So this notion of the split Hodge filtration splitting, is that like something you can express purely categorically? So
Yes.
just given a Calabi-Yau category which is not geometric?
Absolutely. You do not need, in fact, it to be Calabi-Yau. Any category, any DG category, you can define. So I didn't have time to explain, but the notions that you care about are Hochschild homology and cyclic homology. And if the category is smooth and proper, which is some categorical notion which encodes the fact that the Calabi-Yau manifold that you started from is smooth and proper. So for smooth and proper categories, it's a theorem of Kaledin that the spectral sequence that you have from Hochschild homology to cyclic homology degenerates at E1 page. And that induces a filtration on the cyclic homology. And splitting that filtration is the non-commutative analog, the categorical analog of the Hodge filtration in classical splitting the Hodge filtration in classical geometry.
Thanks.
Yeah, so all the concepts, I've worked with geometric concepts here, like for elliptic curve. But if you replace the elliptic curve by its derived category, for example, there is a completely analog notion involving Hochschild and cyclic homology that corresponds to that short exact sequence.
Great. So due to the time, so let's thank the speaker again.